In this video, we will introduce some of the basic ideas used in the topic of errors and measurements. In this lesson, we will look at what does it mean by the uncertainty of a measurement, what causes uncertainty in measurements, how many significant figures and decimal places do we use for the uncertainties and their associated quantities, the difference between absolute uncertainty, fractional uncertainty, and percentage uncertainty. So, we start by understanding what does it mean by the uncertainty of a measurement. A measurement is always never perfect. It is often limited by many factors including an instrument's resolution. For example, a ruler can only measure up to 0.1 centimeters. The experimental method used in the measurement. For example, when measuring the start and stop of a race with a stopwatch, judgment is needed for when to start and when to stop the stopwatch, and hence human reaction time contributes to what is known as the uncertainty of the measurement of the timing. The object itself to be measured could also pose challenges when measured. For example, if you are asked to measure the diameter of an apple, even if you used a vernier caliper, which can read to 0.01 centimeters. Because the apple is not perfectly spherical, where you clamp your vernier caliper will yield a range of values for the diameter. Hence, you see that the uncertainty of the value is not only limited by the resolution of the instrument used in reporting an uncertainty. You need to make judgment on what causes the most uncertainty in the reading and what would be a good estimate for the value of this uncertainty. In general, a physical quantity is reported with its uncertainty in this form: x plus minus delta x and its units written outside the brackets. In this case, the big X is the physical quantity that is measured, the small x is the reported value and very often the average. Delta x is the absolute uncertainty and often simply known as the uncertainty. The units belong to that of x as well as delta x. To illustrate further, let us look at an example. Suppose you are asked to measure the circumference of a balloon with a string and ruler. So you use a string, tie it around the balloon, and measure the length of the string using the ruler. There will be many contributing factors that will contribute to the uncertainty in the reading. The ruler has a resolution of 0.1 cm. The string itself has some thickness. Where the string is specifically wrapped around the balloon will yield different results. Variation in positioning the start of the string on the zero mark of the ruler and reading the marking made on the string against the ruler will also give you some variation on the results. When marking the string, you will be using a pen, and the thickness of the pen will also give you some uncertainty in the reading. Suppose your measurement used 30.3 cm, but because of the different factors, you feel that the variation of the circumference could be between 30.1 centimeters to 30.5 cm. Hence, you report this value as 30.3 plus minus 0.2 centimeters. 30.3 cm is the measured reading and 0.2 cm is the associated uncertainty. When you report like this, you are simply saying you are confident that if you should be taking the readings again, your reading will be very highly probable, falling between 30.1 cm to 30.5 cm. Most of the time, if you expect variations in measurement, you will likely take a few readings and average. Then the final reading reported will be the average value. Furthermore, one way to estimate the uncertainty of that reading is to take the maximum minus the minimum of the range of values and divide the result by 2. However, note that this is only one way to estimate the uncertainty in the reading. Note, it is possible that by simply taking 3 readings and estimating the uncertainty based on maximum minus minimum is still insufficient. In reality, we still need to consider the other factors in the experiment to make a best estimate. Note that while declaring a larger uncertainty will result in more values measured falling within our reported range, too large an interval will also likely make any conclusions derived from the experiment meaningless. Hence, estimating an appropriate uncertainty for the measured value is really an art. The next question we will want to address is, what is the appropriate number of significant figures or decimal places that we should use in reporting our measurement and its uncertainty? To address the question, let us go back and look at our previous example where we determined the circumference of a balloon. However, in this case, we're going to adjust one of the measurement a little. Suppose the values taken are now 30.5, 30.2, 30.3. How should we report the value of C and its associated uncertainty? To do that, we first determine the average of C. In this case, when you work out the value on your calculator, you will get an average to be 30.333333 recurring. And tentatively, we will round it to 30.333 centimeters. Next, we compute the new uncertainty based on maximum minus minimum divided by 2. And we will have 0.15 centimeters. But wait, we are not at the end of our story yet. As absolute uncertainties of readings are often estimates, it's not meaningful to report absolute uncertainties to so many significant figures. Hence, absolute uncertainties are reported to one significant figure, and the uncertainty of C should be written as 0.2 cm when rounded off to 1 SF. The uncertainty of C also tells us that the value of C will start varying in the first decimal place. Hence, C should be rounded off to 1 decimal place. In fact, the value to be reported is to be expressed as the same place value as the absolute uncertainty. Hence, we have our final answer for C and its associated uncertainty to be 30.3 plus minus 0.2 with the rounded off value of C to the nearest 1 decimal place, as the uncertainty of C is also in the first decimal place when it was rounded to the first significant figure. In summary, absolute uncertainties are expressed as one significant figure. The value of the physical quantity is expressed as same place value as the absolute uncertainty. In some cases, some uncertainties are reported in terms of fractional uncertainty or percentage uncertainty. These two uncertainties will be important later when we want to propagate uncertainties. The fractional uncertainty is the ratio of the actual uncertainty to the measured value. Hence, to find fractional uncertainty, we simply take the absolute uncertainty and divide it by the value of the quantity. The percentage uncertainty is simply the fractional uncertainty expressed in percentage form by multiplying 100%. We end this lesson by addressing two questions that the students commonly ask. The first question is there a difference between errors and uncertainties? The second question is, so we know that all absolute uncertainties are expressed to one significant figure. But what about fractional or percentage uncertainties? How many SF or DP do we express fractional or percentage uncertainties in? Let us now address the first question. Are errors and uncertainties the same thing? Well, many physicists will use the word errors to refer to uncertainty in a reading or measurement. Hence, sometimes they will say absolute uncertainty as absolute error. However, it is important to look at the context in which the word is used. Sometimes, the word error could actually mean an action or procedure that causes the reading or measurement to be incorrect. For example, parallax error, the incorrect positioning of the eye. In this case, the word error does not imply uncertainty, but rather it is a real error that's made in an experiment. Hence, again, look at the context in which the word is used. For the second question on SF or DP or fractional and percentage uncertainties, we will often express fractional or percentage uncertainties to 1 or 2 SF. Why? Often it is calculated based on the absolute uncertainty, which itself, we say, is an estimate and we express as one significant figure. But it is also often used for propagation of uncertainties for other derived measurements made from the original raw measurement. If we keep rounding off too much, we ourselves may become the source of error and may unnecessarily produce more uncertainties to the final value that we want. Hence, we will often use 2SF as well. My personal preference is therefore 2SF. With this, we've come to the end of our lesson to the basics of errors and uncertainties. Thank you.